Tesla and Waymo want the same driverless future, but they made sharply different bets about what a car must sense when no human can rescue it. Tesla asks cameras and AI to reconstruct the scene. Waymo adds lidar and radar, giving its driver overlapping measurements. That extra hardware can look wasteful until conditions strain one sensor and no human is ready to take over. Here is the short answer. Waymo has stronger driverless evidence today. That does not make camera-led autonomy impossible. The reason lies in the expensive climb from 99% reliable to 99.9 and beyond. Tesla's approach is camera-led. Here, camera only means its main way of perceiving the outside world, not that the vehicle uses no other onboard information. Waymo also uses cameras, but adds lidar to measure three-dimensional distance and radar to measure range and speed. Both bets make sense. Fewer sensor types can reduce hardware cost and complexity. Tesla's deeper bet is that standard camera hardware across a huge consumer fleet can generate more training data and could scale faster. Waymo accepts more hardware for measurements with different strengths and failure modes. But what product are they proving? Tesla's widely available full self-driving product is officially supervised. The human remains responsible. Waymo carries riders without a human driver inside defined areas. Assistance and rider-only operation demand different levels of reliability.
Let's model what changes when the human leaves the driver's seat. Waymo co-CEO Dmitry Dolgov starts with a person stepping onto a dark road. A camera may infer the shape across several frames. Lidar measures three-dimensional structure directly. Radar adds another way to measure range and motion. None is perfect. Cameras can struggle with darkness or glare, and lidar can degrade in some weather. Different measurements can reduce how much the system must guess. Now the reliability problem becomes clearer. He calls the reliability problem the exponential ladder of nines. On the same defined task, moving from 90% reliability to 99% removes 9 out of 10 remaining failures. Moving from 99 to 99.9 removes 9 out of 10 again. But the failures left behind may be rarer, stranger, and caused by completely different problems. Dolgov says Waymo's early autonomous driving demo took about 18 months. The product journey he described took about 15 years. His lesson: a working demo may be only 1% of the work. And here is where the Tesla Waymo bet becomes dangerous to judge too early. Imagine one technology curve rising quickly, then flattening below the line the product must cross. Another climbs more slowly but reaches it. Judge them by the demo, and you may choose the wrong curve. That is Waymo's case, not a controlled experiment proving Tesla must fail. More sensors add cost, calibration, maintenance, and their own failure modes. Better camera models may keep closing the gap. And Waymo's results come from an entire system: software, maps, simulation, carefully chosen operating areas, validation, and fleet operations, not sensors alone. So, who was right? Waymo's own analysis reports 220.6 million rider-only miles through March 2026 and 94% fewer serious injury or worse crashes than its human benchmark on surface streets in its operating cities. The result depends on road mix and methodology, and Waymo says the comparison is not perfectly apples to apples. Tesla's own report claims fewer major and minor collisions when supervised FSD is engaged. Tesla also reported about 1.7 million paid robotaxi miles through March 2026 and said Austin was ramping unsupervised operation. But Tesla does not disclose how many of those robotaxi miles were rider-only, and its supervised FSD collision categories are not comparable with Waymo's injury categories. Consumer FSD remains supervised. So Waymo currently wins the public evidence comparison. But the data cannot tell us how much of that lead comes from sensors rather than the rest of its system, and it cannot prove that Tesla's architecture will never cross the same line. When you see the next spectacular AI demo, ask 4 questions. 1. How reliable must the real product be? 2. What does one failure cost, and can a human undo it? 3. When its main input becomes weak, Can the system get useful information another way? 4. Is the evidence a curated demo, a realistic test, or unsupervised use in the real world? The same test applies to cars, AI agents that can spend money, and robots working beside people. The harder a failure is to undo, the more real-world evidence you should demand. That leads to our next episode: which AI tests actually predict real-world behavior? If you like finding the hidden rule beneath the technology story, subscribe. Because the best technology curve is not the one that rises fastest. It is the one that reaches the line that matters.